Okay, so now we're going to move on to talk about one of my favorite topics again. We're going to use dummy variables and logistic regression. And I'm hopeful that if any of the previous two lectures was confusing to you, I'm hoping that this helps make everything make more sense, because I think it'll be easier to look at in the context of dummy variables and categorical variables. So let's give this a shot. So, as I say here, I think you'll see some close similarities between what we're going to do here and what we talked about in Chapter 4C with dummy variables. And so I'm going to actually just jump right into a multiple logistic regression model with two categorical variables. Here's the example I'm going to use. Sample of people who come to a walk-in health clinic and require a catheterization, which is, I say, a minimally invasive, but of course anything that's invasive could be problematic. But it's a minimally invasive procedure to check how your heart's doing. We're going to look at the presence of coronary artery disease is going to be our response variable, so it's going to be present or not, disease or no disease. And two explanatory variables, sex, so male and female, and electrocardiogram or ECG measurement, which we're going to divide into high and low. Typically a high ST segment depression is bad and low is good. So we'll see how that plays out. And here are the data. So the data are in this frequency table, which again you could get in SAS using proc-freq. You could do proc-freq. In this case, we have three categorical variables: sex, by ECG, by disease, or by CAD, I think I called it in the data set. So here are our observations. So we have 33 plus 27 is 60. We have 78 total observations here, divided into disease and no disease. For each of our four possible combinations, we have female with low ECG, female with high ECG, male with low ECG, and male with high ECG, diseased or no disease. Okay. So in order to deal with these, just like we did with multiple regression, we're going to need to define some dummy variables to be able to include these categorical variables in our model. And both of these categorical variables have two levels. So I'm going to need one dummy variable for each of these. I'm going to define male to be 1 if sex is male, and male is 0 if sex is female. And I'm going to call a variable high, which is 1 if we have an ECG bigger than 0.1 ST segment depression, whatever that means. And high is 0 if we have a low ECG on this particular. When you talk about ECGs, there are many different things that you can measure, and I'm definitely not an ECG expert, but this ST segment depression is one thing that is measured on an ECG. Just for your own information, here's a picture, a graph that I got off of Wikipedia, and so the ECG measures the wavelengths, the electrical wavelengths produced by your heart, and there are many different things that you can measure. There's these different points on the ECG that are measured: P, Q, R, S, and T. And what we're looking at in this particular data set is the ST segmentation. That's one thing that might be of interest to researchers if they're looking at whether your heart is working correctly. So I just wanted to point that out because I thought it was interesting. It's always good if you're a statistician. The fun thing about being a statistician is, one fun thing about being a statistician is you get to learn a lot, or learn a little, I should say, about a lot of different things. I know very little about ECG, but I do know that there are these different things that we can look at. I don't know what they all mean. At one time I did know, but now I don't. Anyway, continuing on here. So I'm going to define these two dummy variables, male and high. And again, I'm going to let P of X represent the probability of having coronary artery disease, or CAD, for someone with a specific set of X, and here I'm calling X sex and ECG. So I'm actually taking some liberty with notation here. I'm just going to call it P of X when I really have two X variables, sex and ECG. So that's considered a following logistic regression model. Remember, the linear model was modeling the logit of P of X, or the log odds, P of X over 1 minus P of X. And my model is going to be simple here. It's beta 0 plus beta 1 times male plus beta 2 times high, where remember that male and high are both 0, 1 variables. So based on this model, we can actually write out the log odds of coronary artery disease for each of our 4 combinations. Or I'm just going to jump into the odds of coronary artery disease. So for females with low ECG, both male and high would be 0. So the odds of coronary artery disease for females in this category would be e to the beta 0. Okay, because both of these terms would drop out. For females with high ECG, the male term is still 0, so we don't have beta 1, but now high is equal to 1, so we do have beta 2. So for females with high ECG, the odds would be e to the beta 0 plus beta 2. For males with low ECG, males is now 1, but high is still 0 because we're talking about low ECG. So the odds for males with low ECG would be e to the beta 0 plus beta 1. And finally, the odds for a male with a high ECG would be e to the beta 0 plus male is 1, so plus beta 1 plus, and again, high is 1, so plus beta 2. So again, just to help you think through all this, here male is equal to 0, high is equal to 0, male is equal to 0, high is equal to 1, male is equal to 1, high is equal to 0 here because we have low ECG, and finally male is equal to 1, high is equal to 1. Okay, so these are the odds, and remember that, so if we convert them now to probabilities, remember that probability is equal to odds over 1 plus odds. I think I've written that several times now. So if the odds is e to the beta 0, then the probability from this model is e to the beta 0 over 1 plus e to the beta 0. And remember, this is our population model. We're dealing with betas here. No data yet. We haven't done anything with the data yet. So according to our model, this is the probability of having coronary artery disease for specific sex and ECG combinations. So this is the probability of having CAD for females with a low ECG. Similarly, according to our model, the probability of having CAD for females with a high ECG will be e to the beta 0 plus beta 2 divided by 1 plus e to the beta 0 plus beta 2. And the probability of CAD for males with a low ECG would be, my odds are e to the beta 0 plus beta 1, so it would be e to the beta 0 plus beta 1. All of that is in the exponent, by the way. Divided by 1 plus e to the beta 0 plus beta 1. And finally, for males with a high ECG, it would be e to the beta 0 plus beta 1 plus beta 2. All of that is in the exponent. Divided by 1 plus e to the beta 0 plus beta 1 plus beta 2. Again, all of that is in the exponent. So I hope this makes sense. And let me just leave this table up, see if I can put this all on the screen at one time here. Based on these results, and I guess they're not really results yet, this is our model. So based on this model in the above table, what is the model predicted odds ratio? So now we're talking about odds ratios for comparing females with high ECG to females with low ECG. And when I usually write this, I'd say comparing this, I would think of as my numerator. It doesn't really matter which way you do this, but the way I like to do it to be consistent is whatever I put first, I usually put in the numerator, and this I'm going to put into the denominator. So females with high ECG, I want the odds ratio. So an odds ratio is a ratio of odds. So my odds for a female with high ECG is e to the beta 0 plus beta 2. The odds for a female with low ECG is just e to the beta 0. And I'll write this out. You don't always have to write this out, but just to remind you of working with the exponents here, this is e to the beta 0 times e to the beta 2 divided by e to the beta 0. These terms cancel out. So the odds ratio for comparing females with high ECG to females with low ECG is just e to the beta 2. And just to remind you that beta 2 is the term that is attached to high. So that makes sense in this case. So based on the results in the above table, what is the model predicted odds ratio for comparing males with high ECG to males with low ECG? Well, the odds for males with high ECG, e to the beta 0 plus beta 1 plus beta 2. That's males with high ECG. Males with low ECG would be e to the beta 0, that's a beta, plus beta 1. Males with low ECG, the odds of getting CAD is e to the beta 0 plus beta 1. And again, I'll write this one out. E to the beta 0 times e to the beta 1 times e to the beta 2. I'm just expanding this exponent. If you add in the exponent, that's the same as multiplying. E to the beta 0 times e to the beta 1. Then e to the beta 0 over e to the beta 0 cancels out. E to the beta 1 over e to the beta 1 cancels out. And we're left with, again, e to the beta 2. So it's the same thing that we got for the females. Again, comparing males with high ECG to males with low ECG in this model is e to the beta 2. So in this model, does the odds ratio for comparing high to low ECG depend on sex? No. It's e to the beta 2 for both sexes. This odds ratio is e to the beta 2 for both sexes. In this model, do you think that the odds ratio for comparing males to females depends on ECG? Well, we can check that out very quickly. For low ECG, so comparing males to females with low ECG, we have males with low ECG would be e to the beta 0 plus beta 1. Females with low ECG would be e to the beta 0. And we can cancel things out, and that just turns out to be e to the beta 1. And then for high ECG, we have e to the beta 0 plus beta 1 plus beta 2 divided by females with high ECG is e to the beta 0 plus beta 2, right? So we can cancel things out again. Again, that's e to the beta 1. So no, the answer here is that the odds ratio for comparing males to females is the same whether we're talking about low ECG or high ECG. So it does not depend on ECG. But note, it does matter that we're comparing males and females with the same level of ECG. So again, this is what we mean when we talk in these models about holding all other variables fixed. So holding ECG fixed, comparing males to females, leads to the same odds ratio. But the odds ratio itself does not depend on ECG. So let's look at this in SAS again. So again, here are the data for entering these data in SAS using summary stats. So again, this is my input data set if I want to put in exactly this table. So this table again breaks the data set down into sex and ECG. So we have 4 different combinations of sex by ECG, disease and no disease. And so my data set, I'm going to have a sex variable, an ECG variable, and a CAD variable, coronary artery disease variable, and then a count. So the first cell of the table, we had 4 females with low ECG who had disease, and that's what I'm showing here. We have female, low ECG, which I'm indicating as less than 0.1, and coronary artery disease. I'm having a hard time with that. I'll just say CAD, and there were 4 of them. And note that sex, ECG, and CAD are all text variables in my data set that I'm creating here. Again, I'm using the @ symbol, and then I'll enter the next cell. Females with low ECG and no CAD, and there were 11 of them in my table. So I'm just entering the table data directly into my data set. And then I can use proclogistic to run the model. So proclogistic data equals CAD. Again, I have to use freq count because I'm entering my data as summary stats or as counts. And again, the count is my variable name. Remember that count is my variable name. I don't have to call it count, but I did here, and that makes sense to me to call it count. You can call it whatever you want. I'm going to put both of my explanatory variables in the class statement, and I'm going to set the reference levels for both of them. I don't want SAS to pick the reference levels. I'm going to set the reference levels. You could let SAS do it. Remember that if you use a class statement, SAS will do everything alphabetically. And it turns out that SAS also, by default, will pick the level of your response variable alphabetically. So if I didn't specify anything for the level of my response, SAS would model the probability of no CAD, which is fine as long as you know that. You have to know what SAS is modeling. I wanted to model the probability of yes CAD. So my reference cells for my explanatory variables are female. That's going to create the dummy variable male equals 1, female equals 0. And ECG, I'm using the low ECG as my reference category. That's going to model high ECG equals 1 and low ECG equals 0. And then we have to use this extra thing in proclogistic, or I'd recommend using param equals GLM, because that's going to make it familiar for you. This is going to use similar approach to explanatory variables as in proc GLM. So it's going to look familiar to you as it did in proc GLM. If you leave this out, you will get weird results. And I'm not going to explain here why you get weird results. It uses a completely different parameterization rather than 0, 1. It uses -1, 1, which is completely antiquated and nobody really uses that anymore. So then I'm going to model events equals yes, and I'm going to have sex and ECG in my model, and I'll talk about the confidence levels later. So let me run this quickly in SAS. Close this. And my data set are here in the CAD data. Here are the same data that I have in my nodes. Pop them into SAS. And I'm going to run proc logistic data equals CAD. Class sex reference equals female. I'm going to make female the 0 level. And ECG reference equals, and here I'm going to make the lower value the reference level. So I'm just copying and pasting from there, from the data set. And again, we have to say param equals GLM. That's asking for the same parameterization that's used in GLM, which again I highly recommend because that will make it meaningful to you. And I'm going to say CAD event, I can't spell today, event equals yes. So I'm modeling the yeses, sex and ECG. And I'll ask for confidence levels for the parameters. We had talked about that before, so I'll just go ahead and ask for that. So if I run this, I get lots of output. And what we're going to focus on first are my parameter estimates. So let me go back to the notes because all of this output is actually in the notes.